Well, I might as well start. My name is Arthur Lowery. I'm an old professor in electrical engineering, and I'm the unit coordinator for this course. Monsieur is actually going to give you the lectures, so you'll have the pleasure of his company. And we have some demonstrators in the labs as well. Essentially, you can contact both of us, or either of us, or none of us if you have problems. The content is Monsieur's side. I can sometimes sort things out, though timetabling is always a difficulty for anybody. And we'll be having regular meetings just to see how the course is going. This is Advanced Electronics Design. When I was young, electronics design was all analog, and there wasn't much digital about. When I was at university, microprocessors were starting to come online, and people were telling us everything's going to be digital. And actually, a lot of things are done digitally nowadays because you can change it very easily, and computers are so fast. However, there are areas of electronics which are extremely important, which require analog design, and that's what this course is about. So if you're going to do radio transmission or optical communications, transmitters and receivers, fast test equipment, radar, you really need to know what's in this course. And in advanced electronics design, the time delays along wires become important. So a wire isn't just a perfect connection between two nodes. It's a delay. And that delay changes the phase of the signals. So signals that you think are going to be in phase go out of phase. That might be a problem. And it also means that the wire has a thing called a characteristic impedance. I hope I won't do the whole course now, but characteristic impedance is really important because if you've got a cable with a characteristic impedance of 50 ohms, which is a ratio of its inductance and capacitance, and then you go into a cable that's got a characteristic impedance of 100 ohms, you get reflections. And this can be good or bad. We get reflections on our spectacles and reflections out of the car windscreen because there's an impedance change. But we can also use those reflections to form resonators. So you have a reflection here and a reflection here. Then waves will bounce backwards and forwards. So it's all these sort of techniques relying on the delays in circuits and using those delays and perhaps cancelling them out, which are covered in this course. There's also active elements like transistors, which can go up to many tens of gigahertz in frequency, but you also have to consider things like their capacitance and balance this out with inductance. There's also some very interesting things towards the end of the course on converting one frequency to another using things called mixers. And these essentially are very fast switches, but there are different types of mixers that give you different frequency outputs. And these are all critical in your mobile phones. Here's my terrible old mobile phone here, which I get annoyed about, but it was cheap. And the battery lasts a long time. All these techniques are important in that. But furthermore, I used a lot of these techniques in my PhD to simulate lasers. So make computer models of lasers, because a delay is like a memory element. You put a voltage in it, you haul it out later. And in my case, I formed that into a global company called VPI Photonics, which supplies many people around the world, many thousands of people, with tools to analyze optical circuits. So you think you're doing a course on advanced electronics design. However, the theories of time delays and how you treat them also apply to optics. They also apply to hydraulics, so water hammer in pipes and dams bursting and things like that. And you can apply the same sorts of ideas to many things in life. pumping away. The aorta is like a big inductor. All this is essentially the same theory. So please learn, enjoy, think about it, and have a good time. Over to you for the real course.
Thank you very much.
Right, I'm on building 35, second floor, room 204.
Yep. Okay. All right. So I was expecting more than this, but yeah, it's good for me. Good afternoon, everyone, and welcome to Advanced Electronic Design. So just to check that you are in the right place. So this is the first lecture for ECE 5882 and ECE 6882. So I'm expecting some of the masters and some PhD students from electrical engineering. As a beginning point, I believe that I would like to ask one question, that is there anybody who is not familiar with Moodle? So fantastic. So half of the lecture is gone. Just as a quick review to your Moodle website, which is the online environment for your learning. So all of the materials, the lecture slides, the lab manuals, and the supplementary documents, the documents that you need for this course, as well as the lecture videos, which is recording, and then you can, for example, watch them afterwards in your private study time, is available in the Moodle website. So the Moodle website, actually, I opened one here on the left hand, the right hand, if I want to put it. Okay. So on the Moodle website, the first part is the unit guide. So one unit guide for 5882 and one for 6882, which is definitely identical. So one of them is for master's students, the other one for PhD students. All the assessment guidelines, the references that you need to follow, and the times that we expect, for example, from you to upload your results, all of them are mentioned in the unit guide. I would follow one of them to check few things with you. So what we have here. So I opened the 6882, and then here, all right. As you already learned, Professor Lowery is the coordinator of this course. So I believe he's the main contact of many issues that you may find in this course. But from the technical point of view, if you have any issue for your labs or for lecture materials, or any complaint about the lectures, or I don't know, anything that you need to discuss, you should feel free to contact me as well. So the Professor Lowery's office is in Building 35, room 214. And then my name is Maziar Forouzandeh, and I'm doing the lecture for this unit. I have a consultation hours on Wednesday and Tuesday afternoon. So Wednesday 1 to 2 p.m. and Tuesday 5 to 6 p.m. It is in building 35, room 110, which is the usual location for the help desk session. So I will be there. If you have any question about any matters, any concerns, please come over there and then we can discuss in a group or in individual. Also, the other people who are going to help you with this unit are our demonstrators. So we have 3 demonstrators for your lab sessions, Mr. Tayang, Mrs. Melika, and Mr. Mohsen. They are all fantastic guys, and I believe you will be agree with me when you met them in person. The other thing that I want to discuss is the schedule for this unit. So the lectures will start from today, and we have 3 hours of lectures in a row on Wednesday afternoon. So from 3 to 6, I believe it's not very pleasant for all of you, and not for me as well, because I don't think that it would be fine to talk about the boring stuff for 3 hours, and then I don't expect that you listen to me at that in that way as well. So at the middle we will have break, 1 or 2, depends on the amount of material that we are going to cover in one lecture. So and then in that break you can just sit up and got some stretch, or go and grab a coffee if you can do this in time. So about 5 to 10 minutes. And then the lab, we have 8 labs, which will start from next week. So we don't have any lab this week. I heard from one of the students that some of you went to the lab on Monday, so I don't know what was the problem, but usually in ECSC we don't have lab in week 1. And then after those 8 weeks, I mean from week 2 to week 9, we have labs, and then week 9, 10, and 11, you have to go to lab and then do the design project. So we have one design project at the end, and I will discuss this a bit later. So the materials that we are going to cover is, they are mentioned here in this table. So today I'm going to do some induction and talking about the administrative stuff, and then I would explain some basics of the electronics and RF electronics. Most of these you already know, but just to have a kind of catch up, and then for those who may forgot from the undergrad time. So we have a very brief discussion about the passive and active design devices in the electronics. And then from next week we will have the real lectures. It doesn't mean that in the final exam we don't have any question from lecture 1, we will have. But the main stuff that we are going to cover in this unit, and the hard stuff, will start from lecture 2. We have, okay, so about the assessment tasks, as I mentioned, we have 8 labs, and each of them have 2% of your final mark, which in total is 16%. And then we have 2 assignments that you need to complete. One of them, the due date is the end of week 6. I mean in the, I believe in 30th, yes, 30th of August. So 30th of August, 11 p.m., you have to submit this. All the assignments and design projects should be submitted through Moodle. So I will not approve by email, I will not approve in hand. So there will be a link, and I recommend you to just upload your design, and do not put it for the last minute that, I don't know, the Moodle has a problem and it doesn't come up, and then you cannot. So please do this to make it equal for all students. There is a link, and then you have to submit it by that time. And then the second one, the due date is end of week 9. So we have 2 assignments. About the assignments, the approach that we are going to follow in this unit is the problem solving. So in the final exam, you need to do the problem solving. You have 4 or 5 questions, generic electronic questions, and then you need to solve the problem. You have, it could be numerical or it could be parameterized. And for the assignments, there are two sections. So you have to do the problem solving and also a kind of simulation that you learn in the lab. So both of the assignments contain these two parts. And then we have a design project. So the group design project will run from week 10, and then you need to submit your design project report by the end of week 12. So the design project is pure simulation. So the software that you learned in the lab, you need to use one of those, one of the simulators, LTSpice or ADS. I will explain about the lab, in the lab, individual lab. I will come in the first lab and talk about these there. But the design project is a pure simulation. You have to capture your data, and then you need to submit your design files and a report. So the design project outcome and evaluation will be your communication skills and the results that you achieved. And it would be 20%. So the labs are running in group, but the assignments are individual. I mean that you need, every single person needs to submit one file, or one file and one result for the assignments. But in the lab, the demonstrators will come and check your results and mark you at the time. So there is no report for the lab. Anything that you need to show, for example, in the software, you need to show the output of your simulation, or if there is a circuit that you have to play and then show the result of that circuit, and you will be marked by the end of the lab. But for the assignments, you will submit, I will check, and then I will mark you and return and give you some feedback on your submissions. For the design project also, it is in group. So the group of 2 persons needs to do one design project. This is similar as a lab. For example, if Mr. A and Mr. B are in the lab in one group, then they are doing the design project together. And at the end, they have to submit only one report, but in the report, you should mention that, okay, which part has been done by which person. For example, Mr. A done the mixer and the LNA, and Mr. B done the, for example, the filters and the oscillators and phase shifters, something like this. I think I forgot to tell you that each assignment has a 7% of your final mark, and your continuous assessment will be 50%, and your examination also is 50%. The important thing is that this hurdle requirement is that you have to receive 45% of each of your hurdles. I mean 45% of your continuous assessment and 45% of your final examination, and in total you should achieve 50% of the total mark to get passed through this unit. So this is very important. I would like to tell you that if you don't do your design project, I mean if you didn't submit your design project, it is very likely that you don't pass this unit. So because this is 20% of that 50%, it is very tricky. So please make sure that if you, for example, get a final exam 50 out of 50, but you didn't submit your design project, you may fail. So this is what I want to emphasize here. And then about the assessments, I think I have something here as well that I can, so I can follow. Yeah, this is what I told you before. And yeah, for the design project, this is the marking determination. So it is very important that you submit a kind of professional report. I mean that the design project is about the design of a complete receiver. So I want you to submit something which is very professional, which you may submit, for example, to your next boss in a company. You designed something and you want to show that, okay, your design is working. So it should contain some theory background, it should contain the results, it should contain the schematics, and if you've done a kind of trick in your design, all of these are valuable. I mean, it's not just a project to finish. It's a evaluation for the sense of engineering, that how good engineer you are in the RF design. The next thing is the references, the text references that I would like to explain here. Yeah, your textbooks, if I want to tell you about your textbook, so we have two references, the Coleman and the Ludwig. So the first one is available online in the Monash library, so you don't need to buy anything. I believe that the lecture slides and the lecture notes is almost enough for getting the required information from this unit. But for those who want to do more study, who are interested in RF design, in RF electronics and engineering, so the first one is available online. Although the second one is somehow available online, you can search and you can find. So maybe the sources are not very, regular, but it is available online. You can go through the academia.edu and then download the second textbook. So there is no need to buy anything. However, the lecture slides and the lecture videos are available through the Moodle, and you can follow those, and it should be enough. For this course, we don't have any tutorials. So the tutorials actually is a part of the lecture. I'm going to solve few questions and few examples in each lecture. Depends on the material that I'm delivering to you. And also the books has many examples and many questions, and it should be fine with that. If we need more examples, we can assign for the week 13. Let's see. Then I can solve few questions before the exam for you to get ready. So the questions that we have are in the class, and the assignments that I'm going to give you, I will solve those as well. So those are very important for the material for the final exam. The next thing, I already covered this, and I already covered this. Okay. The final thing is that we have 3 hours of lecture here, and I thought that it should be very boring. So I add one online quiz for each lecture, and I had 2 reasons. So the first one was to check that who is coming to class, and so for those who are coming to class and attend these quizzes, regardless of what is your answer to the quiz, just attending the quiz and answering the questions. If you attend the class and attend 10 or more quizzes, I mean 10, 11 or 12 quizzes, you will receive 2 bonus marks. And if you attend 8 or 9, you will receive 1 bonus mark. And less than that, so you will not gain anything. So this is something that I wanted to encourage people to come to a block of 3 hours in the afternoon time. And then the other one is that, so the questions is a kind of review from what I taught you or I delivered to you through the lecture. So it's a kind of evaluation on how good I was or how good you received the materials. The quizzes will be available through the website mars.mu. So at the position that I said that, okay, this is the quiz, please go through your smartphones or laptops or anything. I believe everyone has. If not, I can borrow my laptop to him. But you can simply go through your smartphone and answer the question. These are very simple questions and multiple choices, so you just need to say it is A, B, or C, and then I will solve the question for you as an example for the receiving the materials. The other one also I mentioned, the break, and yeah, and we have also 5 minutes of open discussions every lecture to make it more joyful. I will discuss about one thing which is related to the course, but not as a material of the lecture. So I believe this is the conclusion of administrative part. Oh, one more thing is that my feedback to you could be individual, which is, for example, your marks and what I've written on your assignments. Could be in group, that, for example, the demonstrators will come and tell you in a group of 2, or could be a kind of discussion that we will have in the consultation hours, or we could have here in the class. And I believe, as I cannot read your mind, on the same basis you cannot read my mind. So I believe it would be good that I receive your feedback. Do not put it to yourself. Do not keep it for yourself. If you have any concerns about any material, I mean issues for the method of teaching, issues with the lab times, anything, please feel free and give me the feedback. Although we will have a official evaluation at the end of the semester, that I will encourage everyone to participate in that, which is the outcome will be good for the next generation of the students who are going to take this unit. But if you feel that there is something wrong, don't keep it for the final evaluation. Just come, and if it is applicable, we will try to amend that. Yes, I believe this is the conclusion for the first part, and if there is any question, I'm happy to answer. All right, traffic. Everything is good, and I will go to the next. So, why we should learn this? I believe authors already told a lot about this, that electronics is everywhere. So any device that we are using, at least in this room, you see that many electronic devices, from those which are in your pocket, which are on your hand, on your wrist, or which you are using for studying, all of them has electronics. And most of the electronics that we use today, they have a wireless link. I believe maybe in 20 years, most of the objects in the world has a link, has a sensor link, a wireless link. And this is why this course is important. If you look at your mobile phones, at least it has 5 or 6 antennas for different protocols, different link of communication. It has GPS, it has Bluetooth, it has Wi-Fi, it has the LTE, the infrared, the NFC, many wireless links. And how to transmit signal and data through a wireless link is the main concept of this unit. I mean, how an engineer can get a baseband data and then deliver it to an antenna to transmit through the air or through a guided waveguide, and how to receive that. So both of them, the transmitters and receivers. Many applications I already mentioned here, the wireless communications, the cell phones and the base stations, the high power base stations, the sensor networks, the GPS that we have for localization. Most of you have GPS in your cars or on your phone that you use it. The computer engineering. So the computer engineering is not just a matter of digital engineering. As the speed is increasing and the frequency is increasing, then the electronics behavior is changing. So in the digital design also we have to consider these things. And the connectivities that I already mentioned, that you have with most of your devices, and then the broadcasting systems, the TVs, the radios, and the satellites. So all of them are RF electronic devices, and the radars, which are very usual from the military to the commercial radars that, for example, you use in your cars, or we use for the forecasting, weather forecasting, and these things. This is the outline of what I'm going to cover in this unit. The blue part is what we are going to learn, and this is actually the block diagram of a receiver, a complete receiver. So up to the end of the analog signal, we are going to cover in this unit. In lecture 1, I will mainly talk about the basic components, the R, L, C, and the transistors. In the lecture 2, I will talk about what are our goals in a design, in a RF electronic design. I mean, I will talk about few parameters which are our goals. About, for example, the gain, the sensitivity, the linearity, the harmonics, the noise. So these are the parameters that we are always concerned about. And in lecture 3 and 4, I will discuss about the transmission lines and Smith charts, more into electromagnetics, but electromagnetics which is applied to the electronics. In lecture 5 and 6, I will talk about the LNA and the mixer. So these two components I will cover in lecture 5 and partially in lecture 6. And then the rest of the lecture 6 is going to the local oscillator. And for lecture 7 and 8, we have the PLLs. In lecture 9, we are going to design the RF filter and the analog filters. So it's mainly about the filters. In lecture 10, I will talk about the low frequency analog amplifiers and the different type of amplifiers that we have. And in lecture 11, again, I will come back to the lecture 2 and to see that how we met all these parameters that we were after. And lecture 12 will be the kind of conclusion and the review. So starting from lecture 1, any question up to here? Everything's clear? Okay. So in this lecture, I believe what I'm going to cover, all of you mainly know about most of these stuff, but I will talk about them from a different point of view, from an RF engineer, not from an analog engineer only, electronic engineer. So I will discuss, for example, about R, L, and C, but I say that what is their behavior and what will be their behavior in the high frequency, when we are going to the high frequency. So the behavior will be changed and how we can cope with those. And then about the active components, I will talk about transistors. We have diodes as well, but the transistor is the main component that we use in most of the electronic components. So these four actually if I want to so these four components are the basics for electronic. And I will go to cover this. If we look at the If we look at the spectrum, for high frequency, we are going. I would like to separate the spectrum into three categories, which I call it RF, I call it microwave, and millimeter wave. So it depends on the frequency of the application. We can say that this application is in the range of RF frequency, is in the range of microwave frequency, or in the range of millimeter wave frequency. So previously, I mean 20 or 30 years ago, maybe we could only categorize these in the first two. But nowadays, as the manufacturing and also the higher higher intensity of the applications in the lower frequency, then we have to move to the higher frequency for larger bandwidths and for the new applications like 5G, like sensors, like radars that we have in the high frequency. So the first one you already know. For example, your TV is working in 600 megahertz and it is in RF frequency, or many of the radios that you are listening in your car is in RF frequency. Or the wireless LAN is 2.4 gigahertz, or Bluetooth 2.4 gigahertz, and we can say that it's in the RF frequency, or GPS 1.5 gigahertz. And then in the microwave range, so we have again wireless LAN, 5.8 gigahertz. We have some of the radars in the C band, 4 to 8 gigahertz, in the X band, 8 to 16, or K band, up to 30 gigahertz. And a few radars for forecast radars, and these we have in microwave domain. And in the millimeter wave now we are the trending applications like 5G, like some of the scanners, some of the low mid-range or low-range scanners, which are working up to 100 gigahertz or more. The difference between these are the wavelengths. So when your circuit is comparable to the size of the wavelengths that you are operating, then things are going to get changed. I mean that in a simple analog, when you are working 1 kilohertz. So what's the wavelengths for the 1 kilohertz? So what's the formula for the wavelengths? The wavelengths, yes, thank you. So we can say that lambda equals to C over F, and we will see that this C is mainly V, and this V could be different for different materials. Okay? So, and then if I say that my frequency is only 1 kilohertz, and then C is 310 to the power 8, then it is 310 to the power 5 meter. You can see that your circuit is kind of negligible to the size of the wavelengths that you are operating. Even if it is 1 megahertz, still it is negligible. For example, 100 meters is the wavelength, and then your circuit is 10 by 10, or 20 by 20. So it is negligible. So why it is important that it is negligible? Because if we have a point A, and then we have a point B on your circuit, and then we connect A to B, and if we have a signal A1 here, again I can say that I have the same signal at the point B, which is A1, because the phase of the signal does not change. If the A1, if I want to, alright, what I can do, how can I append to this? Okay, if I write that my signal is equals to S naught cosine omega t plus phi, and then I write that this is S naught cosine 2 pi f t plus phi, and then this f is in low frequency, then we can say that, okay, the signal at point A and at point B, they have the same phase, because we are following the Kirchhoff law, and Kirchhoff law say that, okay, if you put a probe here and these two are connected through a wire, then we can say that, okay, V1 and V2 are the same, and the I which is passing through this line is the same as the I which is coming into the node 1, and which is the same as the I which is going out from the node B. But when we are going to the higher frequency, then the laws are different. I mean, then instead of the Kirchhoff law, we are following the electromagnetic waves. And in electromagnetic waves, another component will be added at this position, and then we call it beta Z. And then it is dependent on the Z, I mean the direction of the propagation or direction of the wave, the direction of movement of the wave. And then because of this Z, the phase will change, and then the signal that you have at point A and the signal that you have at point B has this different phases and different values. Because the signal that you have at point A is S0 with the theta 1, and here is S0 with theta 2. You can imagine that, for example, if the theta 1 is 0, your signal is S0. But if theta 2 is pi over 2, then your signal will be 0. So no signal is there. And because of that, the laws are different, and the wavelength is important in the higher frequency. Then the size of your circuit and the size of the components that you are using is important. I mean, then you cannot use a big resistor or a big inductor to use, for example, in your circuit. Then you have to go to a smaller size. Okay. This is a generic example of an RF system. So we have a transmitter. So we have a digital circuit here. So in this digital circuit, you are generating your baseband signal. And then with this DAC, you change it from the digital signal into analog. Then with the mixer, we will learn about that in later lectures. You up-convert the signal to the higher frequency with the frequency that you generate in the oscillator. And then you use the power amplifier to amplify, filter out, and then transmit it. And then you use an RF switch between transmission and reception. And then in the receiver mode, again, you receive some signal, filter it out, amplify it, use it again, another mixer with the same oscillator to down-convert it to the baseband, filter out the higher harmonics, and then again change it digital signal and process. So this is a general system or block diagram that you expect in a RF system. Okay. If we are looking at the front ends in the high frequencies, we have two types of front ends. I mean, we can categorize the front ends RF receivers or transmitters into mainly receivers to the two categories: the homodyne receivers and heterodyne receivers. So at the end of this unit, you have to design one homodyne receiver. I mean, you have to design all these components by yourself for example, a homodyne receiver at 500 megahertz with these specifications that we will learn later. So what you can see here that we have a baseband signal here. So this is your baseband signal, and this is your data. So this data could be a data from, for example, your GPS signal, could be a data from your audio player, could be a data from your, I don't know, your Wi-Fi, any digital data or information that you have. So this data is modulated with a high frequency signal. And then this data will come. You filter out the other harmonics and the rest of the spectrum to reduce the noise, amplify that, and then you will use a set of mixer, one set of mixer to down convert this data to DC. So the problem with this architecture is that it has a big DC component. So this is the main problem with this architecture. But the main advantage is that it's very simple. So it has one set of mixer. You up convert the signal with the same frequency as the signal that you down convert the signal. And the signal, for example, the frequency, we say that the frequency of your LO oscillator is similar to the frequency of the RF signal that in your transmitter somewhere it is up converted. But the problem is that it has a DC component, and to get rid of this DC component which is inside your signal, I mean our data is also a DC, and then you have another DC component because of this. Getting rid of this is very difficult, and it's not possible. But for most of the application, it should be fine. I mean, we can do this with some techniques to remove this, but the sensitivity of this receiver is much lower than super heterodyne receiver. So in super heterodyne receivers, we does not convert the signal into DC. Actually, we have two sets of mixers. So mixer level 1 and mixer level 2, and then we down convert the signal into a signal which is, for example, at IF frequency, and then move to the next stage. So the complexity of this receiver is more than the previous one, but the sensitivity and the performance and dynamic range of this receiver is higher than the previous one. So it is used for many of the applications, for example, for QPSK or OFDMA or other applications. But, and it is consuming higher power. So for those devices, for handheld devices which is working with the battery like your mobile phones, maybe the homodyne receiver is more comfortable. And then we are going to design all these, we are going to design all these components in a basic level. I mean in a component level, which, for example, if you look at the only this part, I mean, for example, if you look at the power amplifier, the only one component that we have here, the power amplifier. So the power amplifier, for example, you can use a BJT transistor to amplify the signal. Then it contains, then for matching this amplifier to your input signal, then you may need a matching input matching network. For matching this to the next stage, then you have another matching network, and then you need to bias the base of this transistor, that we need a biasing circuit here, and then we need to bias the collector as well, and we need another biasing system. So you can see that small block diagram could contains lots of individual components and devices, and we are expecting you to do this in your design project. And then the realization of this on a PCB design, you can see that, okay, this is the realization of that. This is a double stage amplifier. It has one transistor here, another transistor here, and then the DC, the VCC is coming from this point. So this is your RF signal, and this is the RF input, and this is your RF output. And then the gain of this transistor will be defined by the gain of the first stage and second stage. And then between these two, for example, we have some matching networks. For the input, again, we have matching, and then for the output also we have matching. So these are the things, and the biasing circuit or components that you can see in the middle. And this is the realization on the PCB or the component level. As I mentioned you before, what we are following here is the electromagnetic theory. So in the low frequency, the Kirchhoff law is sufficient. So we can follow the KVL, KCL, and done. But in the higher frequency, as the wave propagates, then we have another dimension, and the dimension is the distance. So we have the variation over time and over distance. So this is the difference between the low frequency and high frequency. In low frequency, the variation is only dependent on the time. So we have just omega t. But in the high frequency, we have another component which is very important, and this is the force equation of the Maxwell, the set of Maxwell equations, that the wave is propagating. And if we say that any wave which is propagating through the air is a TEM wave, which is transverse electromagnetic wave, it means that it follows the right-hand rule. I mean that if your pointing finger is the E field, and then your middle finger is the H field, then the direction of propagation is in the direction of your tongue. So the TEM wave is like that, and then we can say that the beta, or the propagation constant, is dependent on the lambda. So based on the frequency of your signal, the propagation is different. And then we are introducing the phase velocity, and the phase velocity is, the formula is here. Again, the phase velocity is dependent on the materials that the wave is propagating. So if it is air, then instead of mu, you can write down mu equals to mu naught multiplied by mu r, and epsilon also equals to epsilon naught multiplied by epsilon r. And for the air, epsilon r and mu r are 1. Okay? So for these two, for the air, these two equals to 1. So the epsilon equals to epsilon naught, and mu equals to mu naught, and then the values are given here. So if you put these two values here, then you will find that it is C, the one that you said, 3 multiplied by 10 to the power 8. And for any medium, we define an intrinsic impedance. And this intrinsic impedance, again, is followed from this formula that I believe you already learned this from your electromagnetic courses. And again, depends on the material that we have. As I mentioned, as the frequency increases, the wavelength reduces to the dimensions comparable to the size of the circuit boards or even individual discrete components. I mean, for example, in 30 gigahertz, so the wavelength is 1 centimeter, and it could be in the size of your IC. I mean, from this size of the IC, this part of the IC, to that part of the IC, the phase of the signal changed by 2 pi. And it means that the signal is totally different in that. And it means that the circuit design and the component should go to the smaller size. If you are looking at the commercial shelf, we have lots of resistors, inductors, and capacitors. So first, I would like to talk about the passive components. The passive components, first of them, and the simplest one is the resistor. You can see that we have lots of these. You see in your circuits, you get from this cupboard on that cupboard, but they are different. Definitely they are different, and particularly in higher frequency, their response and their performance are different. So what we use mostly in high frequency is the thick film and thin film resistors, which are SMD components. And what I showed you here, you can see that the components that we use, all of them are SMD components. Is there anybody who haven't seen the SMD components, the resistor or inductor, before? So in high frequency, we are interested in thick film or thin film resistors. And again, for the capacitors, we have lots of capacitors. You use many of these for example, bypass, for bypass DC, bypass AC, or designing a filter in low frequency. But again, in high frequency, the cheap SMD components, the cheap SMD capacitors is what we are interested in, what we are after. So the other type of components, for example, the tantalum, or for example, the polymer, the electrolytic or polymeric aluminum or the polyesters and the ceramics, we are not interested, and we will see why we are not interested. I mean, in the later slides, I will discuss that why these are not suitable for the high-frequency design. Similar to the inductors, we have many types of inductors in the commercial shelf, but again, these four are those we are mainly using for the high frequency because of their performance and because of the low prosthetics actually for the high frequency design. What time is it? Okay, we can have 5 minutes break and then we will resume on 4. Merci.
SMD in the chips, or what does it mean, the SMD?
SMD means surface mount device.
So sorry, is it a semiconductor chip?
No,
I mean, what kind of a capacitor is it? I've never heard of it. That's it.
I will tell you. Okay, SMD is the different. I will show you that. Actually, you saw one, I think. I can show you here. So the technology is like this. So SMD is like this. So you have a base, and then based on that you have a metal sheet, and then it connects to 2 leads. So instead of having a wire wound or, for example, a foil of a resistive sheet, you have a base of alumina, and then on top of that you have a sheet of resistance, and then 2 small leads to just solder the.
So sorry, is it primarily used for space constraints?
A space, I told you that a space is important because the wavelength is now low. Okay. I mean, as the wavelength is small, so the device size should be small. Okay. Else, for example, from this point to this point, the phase of the signal is changing.
Okay.
Yeah, this is the main concern. Yeah.
In one of your slides, you had the term in wireless communication called ZigBee.
Yes, true.
What is that?
ZigBee is a kind of protocol for short-range wireless communication.
Okay.
So it's a low-power wireless communication, okay. And for example, it has a coordinator and then few hosts actually, or few sensors, and then the sensors are sleeping, and then at the time they wake up and send sensing the data, the local data, and then send it to the coordinator, and then the coordinator is always on. It is connected to a permanent power, and then transmit it, for example, to the net. It's for wireless networks actually, for for low power wireless. Yeah.
Is it used somewhere today, or?
Yes, yeah, many actually networks, sensor networks actually using this and another. I forgot the other name. Another protocol. So these two are mainly used for wireless network. For example, they use this for AMR, automated meter reading. And in automated meter reading, so for example, you have a gas meter, and then you want to gather the data for this gas meter. Time by time, but now, for example, in the old days, someone come and then read the gas meter and write down, and then, for example, this happens every month or every 2 weeks or something. But with this system, actually, because, for example, all the gas meters of one apartment are around, so you can put the ZigBee nodes. They gather the data, they send it to one node, and then this node, for example, connects to a GPRS and then transfer it to that.
So that makes everything easier.
Yes. For local wireless networks and local sensor networks, actually, they use this.
Just in the big diagram that you showed for the antenna, you told that the signal was baseband, but shouldn't it be bandpass? Like at the receiver end, first we get band. Yeah, this one. Shouldn't it be bandpass first?
Yeah, this is not baseband. This is baseband actually. This.
The one generated by the digital circuitry.
I'm so sorry if I said that it's. I mean, this is baseband.
Yeah.
Yeah, this one is baseband. I said this. Okay, I will correct that. I'm sorry if I said that. This is actually the signal, the baseband signal, which up converted to a band pass. Yeah, all right. Yeah, no worries. All right. Shall we continue? All right, guys. Shall we start? You have my voice. I hope so. Yeah. All right. Okay. So before going to the high frequency for the passive components, I just mentioned that what is the low frequency performance of the passive components. You already know from, I don't know, I believe maybe from your high school. So in the passive component, the three passive components, the resistors, inductors, and capacitors, shows this type of low frequency, and we define them by the impedance of the component is impedance Z equals to the resistance plus J reactance. So this is what you know. And then for the ideal resistors, we believe that the resistance is the nominal resistance of the resistor, and then the reactance is 0. So the absolute value or the nominal value for the resistor is R. And then for the ideal capacitor, we say that, okay, capacitor does not have any resistance. It's just a reactive device. And then the impedance is calculated by -1 or 1 over j omega c. And the value, the absolute value is 1 over omega c. And c is the nominal value for the capacitor. And then for the inductance also, we say that there is no resistance, and the reactance equals to omega L. And omega is the work operating frequency. So if we look at a numerical example, for example, at 50 hertz, the absolute value for a capacitor is in the range of teraohm, which we can say it is open circuit. And then for the inductor, it is in the range of microohm, which we can say it is a short circuit. So in the low frequency, the absolute values for the resistance is the nominal value. For example, if we have 100 ohm resistor, the absolute value is 100. And then for the capacitor and inductors, it is open circuit and short circuit. And in the left diagram, actually, you can see that what would be the value for the different capacitors and inductors based on their frequency, operating frequency. For example, at the frequency of 1 kilohertz, you can see that most of these capacitors shows a very high resistance. And the inductors shows a very low impedance. All right. But when we are moving to the high frequency, what will happen? Let's start from a simple wire. So when we have a simple wire, so you remember from your old school that the resistance of a simple wire, I mean the RDC. I mentioned here DC. It means that it is in DC, in low frequency. The RDC equals to, from your high school, we know that RDC is rho L divided by A. All right? So, and then A is the cross section of your, the cross section of your wire. Yes, true. And then A is PA2, and then rho also, we say that is 1 over conductance sigma conductance. Okay? And this is the same formula. So this is your A, this is A, and this is the length of your wire, and this is the conductance of the conductor, which is, could be, for example, copper or aluminum or anything. But when we are going to the high frequency, this is not valid anymore. And we define a new parameter as a skin depth, sigma skin depth, which is dependent on the frequency. And this skin depth reduces when the frequency increases. What's the skin depth? Skin depth means that the distance from the surface that this conductor is still conductor, and the rest, there is no current passing through this area. So all the current which is passing through a single wire is passing through this area, and it drops e to the minus alpha r, and this alpha depends on the skin depth. Okay? So the highest current passes through the surface, and then it goes down exponentially. And then we can, this exponentially, we can model with this skin depth, and we can say that it's like this. So you can see that for example, in the frequency of, in the range of gigahertz, then this skin depth is comparable to the radius of your wire. Then we define two parameters, the R and L, which is, this is the RAC. I want to say that this is the RAC, which is dependent on the RDC of the wire and the skin depth. Also the L, again, depends on the RDC and the skin depth. I can say that in high frequency, the L omega equals to RAC. So these two, I mean, the half of the, it's a kind of roughly estimation and approximation for the definition of a wire in high frequency. I mean, half of the impedance now is reactance. So you can see that in the low frequency, a resistor, it just has resistance, but in high frequency, it has resistance and it has inductance. So both resistance and reactance we have in the high frequency, and half-half, something like that. Also a wire, so this is a wire, and then when the current passing through this wire I, sorry, I chose right here. When the current passing through this wire I, then it makes magnetic fields around itself. And that magnetic field again makes another inductance. That we call it L external. I mean, then we have two different L from a wire. One coming from the skin depth, that behavior, and the other one coming from the magnetic field, which causing from the current which passing through this L. And this is the value. And when you calculate these two, you will see that the external one is dominant. I mean, when you calculate for example, you suppose you can assume few numbers for the A and for the skin depth and for the frequency, and for the L, and then you can find that what's the value for L internal and for L external. Also, you can look at your book. There is an example there. So when we look at this graph, here. So here in this graph, you see that the skin depth of, for example, the copper, because the conductance of the copper is the best in the conductives. So the skin depth of that one is lower. So it's a better conductor for high frequencies. And then, for example, for the solder, for the usual solder, the tin and the lead, so it is much lower than the pure copper. The main idea of this slide is this, that the skin effect pushes the current to the surface of the conductor, and then this results in a higher resistivity in high frequencies. I mean, we have now two components. Okay, what will happen to the resistors? All right, so we have one resistor. So I said that this is what we interested, the thin film or a thick film resistor, which is the first one. So a SMD thick film resistor, one of your friends just asked that what is the SMD? SMD means surface mount device, or SMT, surface mount technology. So the SMD resistors has a base, so this is the base, which is usually a ceramic like alumina, and then it has a resistive sheet, I mean this part, on top of that. So based on this resistive sheet, we can define the resistance of this resistor. And you know that how we can change the resistance of this resistor by changing the width of this resistor. I just told you here that by changing the A, we can change the resistance. So by changing the width of that ohmic sheet, then we can change the resistance of this resistor and make, for example, 100 ohm resistor or 1 kilo ohm resistor or 1 mega ohm resistor. And then it has two leads at the end to just solder it, for example, to your PCB, to your pads on the PCB design. So if I want to model this in high frequency, so we have an ohmic sheet and I will model it with this R. And then it has two leads here. And then these two leads, I just told you that they show kind of inductive performance in high frequency. And then I can model these two leads as these two inductors. So these two inductors are the inductance of the leads. And this resistor is a kind of resistance of the ohmic sheet and the resistance of the lead together. But the resistance of the leads are kind of negligible to the, for example, value that we have here. Because the resistance of the leads is, for example, in the order of milliohm or micro-ohm, but the resistance of the sheet, for example, 100 ohm resistor is 100 ohm. So it is 10 to the power 4, 5 times higher. And then we have two sources of capacitors. One between these two leads. So assume that we have a conductor 1 and then the conductor 2, and then between these two conductors, we have a dielectric, which is this alumina. So it makes a capacitor. Does it make sense? So we have two sheets. Assume that we have two sheets to these two leads, and then between these two, we have that substrate alumina, and it generates a capacitor. And then this is the capacitance of CB. All right? And then we have another charge separation capacitance. You can look at your book. It has a big theory behind this. You can look at your book. It is discussed there. And then there is another capacitance that we can say that this ohmic sheet itself makes this capacitance. Okay? So this is the model that we have for a high frequency model for a thick film resistor. You can see that it's not a pure R anymore. So the performance of this in high frequency definitely will change from what we expect in low frequency. And we will see in the below graph, I will tell you. And then look at another resistor, for example, a wire wound resistor. Again, we have two leads, two big leads, and then these two big leads give you two big L. And because of these two big L, then the resonance, self-resonance of this, I will tell you that what's the self-resonance. The self-resonance of this type of resistors is very low. I mean that after self-resonance, we are not interested in any device anymore because the performance and then they show different performance. For example, you put a capacitor, and then after self-resonance, it's inductor. So you cannot use it anymore. So the components are mainly used before their self-resonance. Because of these two big leads, we have two big Ls, two big inductor. And it is a wire wound. So wire wound, actually, wire wound resistor, I can tell you that it's like this. Okay. And then this wire is surrounding the core. And this core, I already showed you here that this core could be, for example, air, could be a ceramic, could be different, man, could be I can show you again here. Oh, I didn't show this. Could be a metal oxide, or, for example, could be a ceramic, different materials. And then again, it shows another L, which is this L. It's like a coil. So this coil has a L. It shows a L. Also, it has its nominal R. And you can see that because of this distance, which fills with some material, and we have one conductor at this point and one conductor at this point, again we have capacitor. So two round of conductors, and then there is another material, isolating material between them, and then it shows a capacitance. So again we have this stray, we call it Windings stray capacitance, which modeled with this C1, and again between these two metals we have one dielectric which shows another interleaved capacitance. And this is the model for the wire wound resistors. So as I told you, because of these capacitor and inductors inside the component, this device will have a self-resonance frequency. Why? Because the value, for example, for all the capacitors here is, assume that for the second design, okay, I told you that the L external of these leads are higher than the L internal. So assume that we just have the L external. And then also this L only is the dominant L of this circuit. I mean that I omit this one as well. And then for the capacitors also, the value C1 is much higher than the value C2, because the distance between these two metals is much smaller than the distance between these two metals. So the capacitance between these two strips or windings is much higher than the capacitance between the lead 1 and lead 2. Okay? So we simply can define the impedance of this resistor as this value. We have one L, which is L2, I mean the addition of L, these two L, and then 1 over, I mean this resistance in parallel with the capacitance C1. Okay? Does it make sense? Yes? Or you are right, it should be C1. I will correct it. Actually, in the top model, it is CA. In the lower is C1. Yes, it could be. Yeah, for the lower, it could be C1, and in top model, it's CA. So CA is again dominant. In the top model, also CA is dominant comparing to the CB. All right? No, because so C1 is dominant because the distance between these windings stray, you can see that it is very small here. So what's the source of C1? The source of C1 is this. Okay, so I just want to explain this. All right, the wire wound resistor is like this. Okay. So here, actually, and here we have L, correct? Because we have two wires, and they generate magnetic fields, and we have L done. Here we have a conductor, and here also we have a conductor. So I mean, we have one sheet, one ring, and then another ring, and then a distance between these two filled with insulator, which is ceramic or air or anything, okay? And then you remember that the capacitance equals to epsilon A over D, and D is the distance between the two sheets, and A is the surface of these two, which is the surface of the ring, and epsilon is the permittivity of the insulating material. All right? So for here, for each of these, so this is 1C, this is 1C, this is 1C, and then all these together, I call it C1. Okay? And then again, oh my God. Sorry. Just this. Okay. Sorry. And then again we have one conductor here and one conductor here. Okay? So between these two conductors also we have one C, and I call that C2. So the distance is higher, so distance of the second one is higher, so the capacitor is low. So this is why we say that C1 is dominant. Yeah. So this circuit has a self-resonance frequency, and where the self-resonance frequency is where the impedance of
What resistor has self-resonance frequency?
any resistor has a self-resonance frequency, but the problem is that as the wire wound resistor has higher L, the value for this L external, because of the type of the lead and because of the type of the coil that we have inside, the value for the L is higher, then the resonance frequency shifts to the lower frequency. And after resonance frequency, then this device is not resistor anymore. This is what we have.
External is L2 here? Or
Yes. L2, actually L2 is the addition of L external and L internal, but L internal is very, it's negligible to the L external. But what I showed you before. Just I want to, yeah. Here we have in wire wound resistors, we have three sorts of inductors. L external of the lead, L internal of the lead, and the L causing from this coil. This coil, we have a coil. So we have 3L. So the third L, the third one which causing from the coil is L1. The addition of the L internal and L external is L2, because both of them are sourcing from the lead. Make sense? Okay. So if we solve this equation that we have here, you put some numbers, and then you will see that in one point, the value for the resistor will reaches to very small value, which is 0. And this is the resonant frequency. And that value is actually equals to omega equals to 1 over square root of LC. Okay? So from this frequency, and this omega is 2 pi f, from this frequency, then it shows that it has the inductive effect is dominant. Near this frequency, lower than this frequency, but near to this, it shows that it has a capacitive performance. And then in the low frequency, it is resistant. So for example, up to this point, we can say that, okay, it is still capacitor, because still resistor, because the resistance performance is much dominant comparing to the other two. Okay? And from that point, then it is not. It's something else. Okay? For example, for a thin film resistor, a 2K thin film, 2 kilo ohm thin film resistors, so the resonance frequency is in the order of hundreds of megahertz. So, for example, up to 100 megahertz, we can say that, okay, good. Up to 100 megahertz, I can use this. But if you want to use a resistor, for example, in, I don't know, 1 gigahertz or 10 gigahertz, then you need to move to the better technology than this. So these thin film resistors, as I showed in the previous slides, has different sizes. You can see different size. So the smaller values shows a smaller L, shows a smaller C, and then the resonance frequency can move to the higher frequencies. Inductors. So what I told you is exactly here. So inductors, again, you see one inductor here. So this inductor in low frequency. So in low frequency, the inductor has a inductance which comes from this coil, and then it has a very negligible amount of resistance because of the resistance of the wire. And the resistance of the wire we already calculated as rho L over A. So the value is in the order of milliohm or ohm, depends on the number of turns that your coil has. But in high frequency, again, we have this capacitance CD, which is what we don't like, and it's there, it's always there, because even in the SMD inductors, which I showed you here, so SMD inductors, you can see that they are making out of coils. You see that this is coming, and then there is a coil, and then it goes out. So the core only is different. And here in the ceramic also, the windings are inside this. Okay? And here also, for example, for the ferrite core, the same thing. So most of the inductors are based on, in high frequency, are based on solenoid structure. So in high frequency, again, if we want to model this inductor, we have one inductor, which is the nominal value for our inductor, and it shows a series resistance, which is based on this RD. I mean, if we say that the RD is the distributed resistance, then that's RS, which I found here, is a combination or composition of this RD, and then we have a distributed CD, and then at the total it generates a CS for you. All right? Again, we have a self-resonance frequency because we have an inductor and we have a capacitor. So unfortunately, we have a self-resonance inductor. And because of this formula, now your impedance will be very high at the self-resonance frequency. So in one point, you will, I mean, the absolute value of your impedance would be very high in the self-resonance frequency. If we look at the performance of an inductor, so it is J omega L. I mean, by increasing the F, the value for the impedance should increase linearly. It is linearly, the value of the impedance is dependent on the frequency. Lower frequency, lower impedance, higher frequency, higher impedance. Okay? But when we have these nonlinearities and these parasitics inside the inductor, then the performance changes to the new graph. At one point, again, we have self-resonance, and after that, the performance is not like inductor, it's like capacitor. Because the impedance is dropping. By increasing the frequency, instead of the impedance is increasing, the impedance is dropping. It means that the capacitor here in this region, the capacitor is dominant. Capacitance is dominant. And this is the message for this slide. All right, and the values for the inductors. So the values for the inductors are calculated from these two. For the actually solenoid type inductors, the values are these two. And n in the number is the number of the turns in your solenoid. Mu naught is the absolute permittivity, which is 4 pi 10 to the power minus 7. And then the L is the length of this coil. Okay? So it is calculated from these two formulas based on the condition that we have. The behavior of a RFC. RFC means RF charge. So RF charge is one of the base components for the biasing circuits in RF designs. So as we had here, so what I have here, you see that for biasing circuits, we use RF chucks. Anybody knows why? Because when we are going to bias a transistor, we usually use a resistor. So why we don't use a resistor? We use an inductor instead of bias. I mean, in the collector, we just simply can use a resistor and then bias the transistor. This is what we do in the electron. But why you are interested in inductors instead of resistors? Any?
Because of high frequency.
So why because of high frequency? Well, what's the difference? It could be a combination of these two answers. So what is the performance of the inductor? Inductor, the impedance for the inductor is Z equals to J omega L. All right. So J omega L, and it means that in higher frequency it shows a higher resistance. Okay? So it means that if you have a high frequency signal at this point, then it does not let this signal go through your VCC and then go through your other part of your circuit. It's a kind of filter for you. And in low frequency, it shows a very low impedance, and it can act as a wire, and then, for example, you can bias your circuits based on these components or any other components that. So it is working as a kind of AC filter, and it does not let the RF signal passes through your circuits and make a noise, for example, from this part of your circuit to the other part. If, for example, we use a, 5 nanohenry inductor, and then at the frequency of, for example, 1 gigahertz, 2 pi, then you can calculate that the impedance is 10 pi, yeah. So it shows the impedance of, for example, 30 ohm. And I don't know, for example, true. Actually, 5 nanohenry is not a good value. For example, 50 nanohenry. So 50 nanohenry or 100 nanohenry can give you an impedance of around 500 to 1 kilo ohm in high frequency. And then 1 kilo ohm, I mean the signal that we have, the current that we have here is 1,000 times less than the current which is going to the VCC. This is the main reason that we use RF chucks instead of resistors. Okay. All right, back to here. Sorry, back to, yeah. think I missed this slide, and then I'm sorry. I think I missed this slide. So capacitors in high frequency, as I said, so in low frequency, the capacitance is calculated from this formula. Famous formula, we have two sheets, and then between them there is a isolator, and this isolator has a dielectric constant, and based on this dielectric constant and the absolute dielectric permittivity, then we can calculate the capacitance between these two. It depends on the area of the sheets and also the distance between two sheets. Okay? And also, because of this dielectric that we have here, any material in the world shows a kind of resistance. So this dielectric also has a resistance that we can say that it's like this. This is what we calculated for a wire previously. And now it is a Q. So the sigma of the dielectric multiplied by, again, the area divided by the length. Okay? So any capacitors can model as in low frequency, can model as this. Capacitor in parallel with a resistor. Does it make sense? Okay, and then the value, and then we define a new parameter. The name is loss tangent or tan delta. Okay, so this tan delta is basically used for defining the Q factor of a reactive component, like capacitors or inductors. And it is the unwanted value divided by wanted value. Unwanted value of a capacitor is the resistance, because we like that ideal resistance is something that it shows on the ideal capacitance is something that shows only capacitance. It doesn't show resistance. But definitely because of this material, it has a resistance as well. So we are after that this tan delta equal to 0 always, but it is not, never, ever. And based on the dielectric constant and also the sigma of the dielectric that you use, it could be another value. For example, if you have a capacitor and the dielectric is air, which is a very, very, very good dielectric, then this loss tangent could reaches a value which is very close to 0. But if you use another substrate, or which we use, or electrolyte, or another ceramic, then this value could increase. In high frequency model, again, you have a capacitor. So this is, for example, your capacitor, and it has two leads. And these two leads shows, again, as we already know, shows inductor and resistor. It's just a wire, and a wire shows an inductor and a resistor. And in this inductor, as you know, is external, internal, and the resistance is calculated from the formula that you have. So this is what we model a capacitor in high frequency. And then the key message is, okay, and then the graph. If you look at the graph, what we are looking at a capacitor in ideal capacitor is like this, that by increasing the capacitance, by increasing the frequency, the impedance decreases. So this line here shows the ideal capacitor. But again, because of the combination of these two components, we have a self-resonance frequency, and at this self-resonance frequency, again, the impedance goes down. So before the self-resonance frequency, the ideal capacitors work as a capacitor, and after this, it works as an inductor. It means that the inductor is dominant, and by increasing the frequency instead of decreasing the impedance, we see the increasing the impedance. And we are not interested in this region. So this region is what we are not interested, and this region is the OK region. Okay? So, and I already covered this. Sorry, I think I missed that one. So for the inductors, actually, you see that the behavior of the RF chalk deviates from the expected behavior of an ideal inductance at high frequencies. The impedance increases rapidly as the frequency approaches to the resonance and then decreases because this CS is dominant. All right? These are the different types of the inductors that we have. This is the one that we usually use in the high frequency, and this is the formula for calculation of the inductance. And also we can, in very high frequency, I mean in the chip design, we are making the inductors with this method. And in the next slide, I will show you that this is not something that we are interested in. So this is for very high frequencies. I mean, in the ICs, for example, we don't, if we want to design everything in one IC, so we have transistors, by semiconductors, these things. And then how we are generating a RF chalk inside an IC. So we are using this. And then from here to here, they use a bridge. And then these two are the input ports of your inductor. So just by making a kind of a spiral-shaped conductor on top of your surface, on top of your semiconductor, then they can make an inductor. And then by changing the length of these, by changing the distance between these two, they can manage to achieve different values. All right. And this is a practical measurement of a toroid that I mentioned to you at the frequency of 100 kilohertz only. And it is measured by an LCR meter, HP 4192. It looks old, but I think still this is the best LCR meter available in the commercial shelf. It is fantastic. It's working up to few megahertz or maybe 10 megahertz, but the newer versions, actually, if you can see the mark here is Hewlett-Packard, maybe 1985 or 1990, something like that. And now, then it changed to HP, and now they changed to Keysight. So 3 generations of companies changed. But if we look at the performance of this and measure the frequency response of this toroid, this is the graph. This is the graph. And it is measured up to, okay, it is measured up to 10 megahertz actually. So it is working up to 10 megahertz. And you see that at the low frequency, the impedance, the value of the impedance is dominant. And the impedance is the impedance of the wire that we have. So in low frequency, I said the J omega L because the omega is very small. So the value for the inductor is 0 or something in the range of milliohm or microohm, what we saw before. So this is dominant, and then it shows a kind of inductance behavior. So by increasing the frequency, the impedance increases. Then it shows a rapid increment in the impedance, and then afterwards it drops down because now it shows a kind of capacitive performance because of the capacitor. And then this is the bottom graph is the Q factor. So you can see that near this region, we achieve the highest Q factor that we have, because near this region we achieve the highest J omega L, and the resistor is almost constant. And then, I mean, at this point, we will achieve a Q factor of, I don't know, in the range of, for example, it says that the Q factor is in the range of 20 at 100 kilohertz, which is 100 kilohertz is here. So this is what it says, for example, this point or this point. So here it is 20, the value. Crystal clear. Good. All right, the exercise. So it's time the exercise. I would like you to think about the question for 1 minute. Try to solve it by yourself, and then I will solve the question for you. Okay? So it says that assume that this is the equivalent circuit for a wire-wound resistor, and which is shown in the figure. And assume that the capacitive parasitics are neglected, and the effect is quite small. The wire-wound resistor is composed of 10 turns of wire in the form of solenoid with the diameter of 1 centimeter, length of 4 centimeter, and use the Wheeler's inductance calculation formula to estimate the series inductance of this resistor. And the mu naught is this value. So you have to follow one of these equations. I mean, this is the equation for the solenoid. Also, this is the equation for solenoid, and both of them are the same. And you can use either of them. One thing that I forgot to tell you, and it was very important in the administrative part, is that the final exam is open book. So you can grab everything that you want. You can grab tens of books, your notebooks, any type of calculator, anything. It doesn't mean that the final exam is difficult. It does mean that we are after engineers, electronic engineers. We are not after those who are memorizing things. You should be able to analyze circuits. This is what you have to learn in this unit. How to analyze circuits, how circuits work, and how you should, for example, bias a transistor, how you should match one circuit to another one. And these are not something that you should memorize, because in the real world, after this university, when you graduated, you have your books on your shelf, and then you have to solve the real problems like that. So in the final exam, you will have everything with yourself. So I'm not supposed to give you any information in the final exam additional to what is in the question. I mean, I will not give, if I said that, okay, calculate the inductance of a solenoid, I believe that you have the formula with yourself. This is my, I don't know,
So there won't be a formula sheet.
assumption.
So there won't be a formula
No formula sheet, you have questions and a bunch of books with yourself.
Okay.
Okay? All right, 1 minute to solve this. And as I don't know the result, I have to look at the... Oh, I'm sorry. I can... Because you need the formula, I can go... I'm sorry. These technologies. Okay. So done. What's the value? I think I have something else. I don't know. Why 56 per centimeter? All right. And the length is 4. So it is 225 micro.
0.225.
Nano. All right. Okay. I go this to this slide because I want to write down here. All right. So based on the formula L equals to d squared n squared divided by 0.45 d plus L, and then you have to insert the values. What's the value for d? No, what's the value for d? It's 1 centimeter, which is 10 to the power minus 2 squared, and n is 10, which is 10 to the power 2, and then 0.45, again d 10 to the power minus 2 plus this L, which is 4 centimeter, true? Yes, 4 centimeter. 4 10 to the power minus 2. And the value is 225 nanohenry. Just take care that the Wheeler, the D and L is in meters, but the L is in microhenry. So this is the difference between this formula. I mean, difference between this formula and this formula is that here we have a mu naught, which the value is 4 pi 10 to the power minus 7, and it compares for that micro Henry that we mentioned here. Okay, so if you put into this the values that I gave you, put to this, you exactly reach this number. You can either use this formula or that one, no difference. Okay, so this is very simple, just as a beginning of this lecture. And then so this question, this is the next question exercise that we have. If you want, we can okay, finish this and then we will have a few minutes break, or we can have a break and then all right, let's go. So solve this, think about 1 minute, and then consider a circuit as shown. Note that most transistors won't like a voltage applied directly to the base, where the resistor is wire wound and has an inductance as calculated in exercise 1.1. If the transistor is switched between full load and no load in 100 nanoseconds, assuming that the rise and fall currents are a linear ramp, and then sketch the current and voltage wave. And then do this again for 10 nanoseconds. it's a bit difficult to draw this here, so I will upload the result for this question, and then you can look at that. And I think we are a bit behind the time, so we can have 5 minutes, and then I will start with the transistors. I will upload the solution for this question. It's very straightforward, so it should be fine, but I have to draw some graphs. I think it should be fine. We will resume at 5.
The units of your formula. How does the units work here? If like this is length squared and you have length from the bottom, this is unitless.
Okay. So what I can tell you is that in this formula which is equivalent to that one, so this mu naught, the dimension for mu naught is Henry per meter. Okay. So this mu naught is actually simplified in that formula. So this mu naught is 4 pi 10 to the power minus 7 Henry per meter. So this is where this then L is coming. I mean the inductance is coming.
Okay.
And we simplified that one and say that this is microhenry, and then this 10 to the power minus 7, 10 to the power minus 6 of that is changed to the microhenry. Okay, I mean we can say that 4 pi 10 to the power minus 1 microhenry per meter. This is like that.
Yes.
And then we have M2 in top, and then M in the denominator.
So the bottom formula only works if you use it in meters of if your number is on units of meters.
Yes. So these two are in meters, but the final value is in microhenry.
Yeah.
So if you keep this there and then simplify all these, I mean divide, for example, this by 10.
Yeah.
If you divided this by 10, then you will reach exactly the same value that you have here.
Okay.
And then the final dimension would be microhenry.
Okay.
Yeah.
So in this formula, L and D have to be in meters. The numbers have to be
Yes.
meters.
D and L are in meters.
Okay.
Yeah.
Okay.
But the inductance is in microhenry. Okay?
Yeah. Okay.
Yeah. All right.
So for this formula,
Yeah.
applying to this model, so
This model, no.
just now.
No.
So in this model, it's only this
I think this model is different, yeah. So the Wheeler's actually is applicable on this. I mean, for this model, because in this model we don't have the D. I mean, this model does not contain D. So the distance between, the diameter of your rings here is important, but here is not important. It's different.
So this one's also different.
This one is also different, yes.
It's not gonna apply.
This is applicable for solenoid only, solenoid type inductors, which is mainly the inductors that we are using in the RF electronics. Okay? Yeah. All right. Okay, guys, we shall continue. I think we are a bit behind the time. I want to cover the transistors, which is the active component, and it's very important. One thing that I forgot to mention again in the administrative part is that we will have a different session of labs, but you should go to your labs which is assigned to you in Allocate Plus. So you should not, for example, if you assigned on Monday, you should not go on Friday, because we don't have enough stations there. So it is already full. Okay? So if you have problem with your time, send me an email. 90% I cannot sort it out, but let's see. Okay? We have 2 sessions from 3 to 6 and 1 session from 6 to 9. Okay? Thank you. 1 session from 6 to 9, and it is on Tuesday, and 3 to 6 it is on Monday and Friday. So please do not change your lab sessions because we cannot accommodate extra students. Okay, transistors. We have mainly 2 categories of transistors in RF electronic, BJTs and MOSFETs. Each of them has its own advantages, disadvantages. BJTs are older technologies, MOSFETs are newer. MOSFETs are for low power. They are applicable for mixed design. I mean, in those designs that you have digital signals and analog signals at the same time. Can we continue on this? And then you can discuss later. Thank you. And then when we have mixed design, then we prefer MOSFETs, because most of the logics nowadays are making out of MOSFETs. They are fast. They do not consume power in the steady state. So the only power that they are consuming is in the transient, so it's very good for the low power design. But the BJT also has its own advantages, and the main advantage is in high power design. When you want to make a high power transmitter, then it should make out of BJT, because they can tolerate higher powers. This is what you already know. I just review the basics of these 2 transistors. BJTs, we have 2 types of BJTs, NPN and PNP. So NPN, the junction, we have 2 PN junctions, as you can see here, and each PN junction could be introduced as a diode. So we have a back-to-back diode here at this point. And then we are going to bias these 2 diodes, one of them in forward and one of them in backward mode. And then the current is flowing from collector to emitter. You know this from the basic electronics. So we are biasing the diode 1 in forward mode, and then we are biasing the diode 2 in backward. Done. We have 3 regions for the BJT transistors: the cutoff, saturation, and also the triode modes. And in analog electronics, we are interested in triode. Why? Because in triode, a transistor works as a current control device. Okay? It means that by changing the current of the base, we can change the current of the collector. Very simple. You know from the old electronics that IC equals to beta IB. And this is happening in this region. I mean the region which is not dark. I mean this region, this one. I will tell you that how we can bias a transistor in the BJT. In the MOSFETs, so the topology is different. So in the BJT, actually, if I want to draw the topology in the BJT, it's like this, that we have one N region, and then we have another P region, and then we have another N region, okay? And then we have one lead here, and one lead here, and one lead here. And we call this, for example, your base is, this is your collector. For example, this is your base, and this is your emitter, okay? So the topology is like that. But in this MOSFET, the topology is like this. So we have a bulk, and then we dope those, for example, N or P inside that. So we have a bulk, and then we can make both MOSFET, the NMOS and PMOS on the same bulk. Okay? This is what you know. Again, we have three regions, the linear region, the saturation region, and the cutoff region. Okay? And in this one, we are interested in saturation. We never try to bias a transistor in the linear, in the MOSFET, and we never try to bias a transistor in saturation region in BJT, because we are not as expert as the IBM engineers. Okay? It's very difficult to control the transistor in these two regions. It is fantastic if you can do, but we cannot, okay? Because it moves. Because we cannot find that, okay, the current is at this point or at this point. And if we cannot find the value of the current, then we cannot say that what's the gain of the transistor. We cannot control. But in this region, as you can see, the current is constant. Based on the value of the VGS, the current is constant, almost constant. We can see that there is some effect in the high frequency that changes this. But as the current is constant, by changing the value of the VGS, we can control the current of the collector. Clear? So we can say that this is a voltage control device. By changing the VGS, VC, we can achieve a different value for the IC. Here, by changing the IB, we can achieve the value for IC. Okay? This is the basic. Going into more details for the BJT. So BJT devices, the current follows from this equation. We have this equation from this is the equation which is a principal equation for a diode. You know this equation. The IS is the reverse saturation current of the diode, the diode for the one that we biased forward. And then the VBE is the voltage between the base and emitter. The VT is the thermal voltage and calculated based on the Boltzmann constant, the room temperature, and then the charge of the electron, which is the value of 1.6 10 to the power minus 19. All right? Multiply by, and this value that I show you here is the current for the saturation region. Okay? So this is valid for the saturation region. And multiply by 1 plus voltage between the collector and emitter, and a value VA, which is a number is given from a transistor data sheet, and we call it early voltage. And it's here. If this transistor works as linear, then this VA is the point that this graph is going to reach your IC equal to 0. All right? How we can find the value for IC? So we know the value for VCC. We know the desired value that we want for the VCE. For example, I want to say that, okay, my VCC is 5 volt, and I would like to have this point, which is the VCE, as 2.5, I mean in the middle. Then I can have, so this is your, this is your biasing point, your VCE, and then your signal is going to be here. So I have the maximum dynamic range for changing my signal. I mean, I can amplify the small signal which is coming from the base by maximum gain that I can get, and then I'm not going to get saturated or going to into nonlinear region. So we know that what is the value for VCE we need, and then based on that we have to define this RC. Also, we know that what's the current that we want. For example, I want to bias my transistor with the IC of 5 milliamp, 10 milliamp, 15 milliamp, or 20 milliamp. Then you have to find the value for RC and then bias this transistor. So the biasing actually is the intersection of this line here, this line, and one of these graphs, which is this point. Done? So this line, the equation for this line is this one, and the equation for that graph is this one. So the intersection of these two shows the biasing point of your BJT. So this is in DC, the biasing. Guys, I want you to consider this, that the main thing, one of the main things in the RF transistors and behavior of the RF transistors is the biasing point. So biasing happens in DC, but these biasing points actually gives you most of the parameters that you are after. I mean the gain of the transistor, then the transconductance, all these parameters depends on the biasing. So biasing is the first step and is I believe is the most important one. So you should consider that in any of the applications that we are going to cover, this biasing is there, and you should know that how to bias your transistor in a correct position. The low frequency model for a BJT transistor, again, you had in your electronics. We say that it is like a controlled, current controlled device. So by changing this VBE here, we can change the current in the collector. And then I said that it is current controlled, but here we have VBE, but just understand that this VB equals to R pi multiplied by IB. I mean, by changing that IB, then we can change the current in the IC. So this is what we had in the low frequency. We define one parameter as GM, is the changing of the current in the collector based on the changing of the voltage in the base. So how much change of the voltage we have in the base, and then how much the current of the collector is changing. So this is almost the kind of gain of the transistor that we are after. I mean, I change something in the base and then I receive what in the collector. So this is what important in the transistor, which we call it as GM. And we say that it is the partial differential of IC divided by the partial differential of the VBE. All right? And then by putting those formulas, you can achieve that the GM is IC over VT. This is why I said that the biasing is important. So the value of IC is showing the value of the GM. And we will see in one of the examples that the value of the GM shows the gain of the transistor. Okay? And the connection between the collector and emitter we defined as RO. Okay? And then this RO again is the change of the voltage between the collector and emitter based on the change of the current in the flowing through the collector to the emitter. And again, if you put the values, you will achieve this formula. And if we say that the VCE is much smaller than the VA, the value is again divided by the DC bias current. Clear? Okay. And then we define the input impedance, or R pi, which is again the partial differential of the voltage divided by partial differential of the current. And then this R pi is calculated based on the GM, which is it itself depends on the IC and also the beta, which is the characteristics of the transistor. For example, we say that this transistor, it is something which comes from your data sheet. The beta is, for example, 50 or 100 or 200. So these are the three values that we are defining for the low frequency model of a BJT transistor. And this is a kind of rough assumption or rough calculation, I can say, that GM always much higher than 1 over R pi and 1 over RO. So this is the transconductance, this is the conductance, the input conductance, and this is the output conductance. All right. But in high frequency model, which everything is harder. So as I mentioned here, the model that you have for the BJT, so we have one lead here, and one lead here. All right? So between this base and between this collector, so we have a junction, and this junction has a capacitance. So we have one capacitance between these two, and between this collector and between the base also we have another capacitance because of this junction, and we have one junction here and we have another capacitance here. So two main capacitance we have in the BJT, and this makes our life difficult in high frequency. Why? So we define two capacitances, C mu between the base and collector, and C pi between base and emitter, and then the model changes to this. The effect of these two are in many domains. One domain is just, I put here as an example to you, that the gain of the transistor drops. So as I said, the gain of the transistor is, for example, in low frequency, the gain of the current gain, actually, not the voltage gain. The current gain is beta, and then in the high frequency, you can see that, and the beta is GMR pi. And the high frequency, you can see that the gain drops by the value of that you catch here. I mean, this value will add to 1 and then drops your gain. This is one thing. The dominant, I mean, the major problem that this C mu generates for us is the feedback that happens from the collector to base. I mean, now we have a link here, and there is a feedback. And this feedback could be disastrous in the design of RF electronics, because your signal comes back and then again amplifies and comes back and amplifies and comes back, and then your transistor, instead of working as an amplifier, could work as an oscillator. And done. Then your circuit doesn't work. So you make an amplifier, and then you connect the network analyzer to the output. Without putting any input, you see that, oh, there is a big signal there. So you're oscillating somewhere, and then it's very difficult to solve this. So there are techniques for removing the effect of this. We will see when we are going to design the RF amplifier. This is one of the main things. Also, the value for the C pi, this is a big value here. And then because of this, then matching to the base. I mean, the input matching, there is the need an input matching circuit to eliminate the effect of this C pi. And this we will see in the lecture 5. Okay? The MOS transistors. So the MOS transistors, again, I said that we have 3 regions. You can see that these 3 regions could classify based on the value of the VGS, the voltage between the gate and the source, and the value of the VDS. the voltage between the drain and source. So if the VG, and then in the MOS transistors, the current is calculating based on this formula, and this formula is again valid only for the which region? Saturation region. Yeah. So this is only valid for the saturation region. The value, the parameters W is the width of the transistor. If I want to go back to this figure here, so this is the width of your transistor. This side, this is value W. And you see that if we increase this W, then the current that passes through the transistor is higher. Makes sense. So by increasing W, you can increase the current, but then you increase the size. And then this is the L, and actually we are after L effective because we have a depletion. I don't want to go into the physics of this transistor. Based on the depletion and the coverage of your leads, this L should change to L effective, and this is something that you can follow in the MOS transistor books. And you can see that by increasing the L, then again the current drops. I mean, then the distance between two junctions is less, and the current which passes through the depletion layer would be smaller. So we have W, L, C oxide. So this is the capacitance of the gate. So the capacitance that we have here. So here is a metal, and then here is your bulk, and then the capacitance. And then we have one oxide here, one layer of oxide, which you can see. And then based on this oxide, we have capacitance. And this is the value which is given for any technology of CMOS or gallium arsenide or any other technology. So any of them has one C ox. Okay. And then the mu n is the mobility of the electrons in here, and then in the, for example, this is NMOS, and in the PMOS is the mobility of the holes. Okay, and we know that the mobility of the electrons is higher than the mobility of the holes, and because of that we are more interested in NMOS. This is the main reason that we are interested in NMOS rather than PMOS, because the mobility of the electrons is higher. And also for construction of an NMOS and PMOS on the same layer, you have to make a region for the PMOS to deploy or construct your transistor in that. I mean, the bulk is usually P, and then you have to deploy one N region for that, and then put your P and P in there. But for the NMOS, you don't need that region because the bulk is already P, and you can put two N region and done. And then the VT is, or VT naught, actually, I want to say here, not VTH. I would like to say VT naught because we changed this to VTH later when the higher effect of the transistor is coming. And then this VT naught is the gate threshold voltage. Again, it depends on the parameters in the transistor. I will show in the next slide. We have three regions based on the value for the VGS and VDS. If the VGS is less than V threshold, then no current is passing through your transistor. And it does make sense. I mean, we don't apply any voltage, so no current is going. And then if we apply a voltage which is higher than the voltage threshold of the transistor, the voltage threshold voltage of the transistor is in the order of 0.5, 0.6, 0.7 volt. For the old transistor, and for the newer technology they try to drop it down, then we can run this transistor in lower voltage. Okay, so for VGS greater than V threshold, then we have the triode region if the VDS is less than VGS. So we have some current. I mean, the transistor starts to conduct. Sorry. The transistor starts to conduct, and then after the VDS greater than VGS minus V threshold, then we have the saturation region, and the formula is coming, the current formula is coming from this one. Okay? To find this, it's simply you can put, for example, the VDS equals to VGS minus V threshold, I mean at the boundary region, and then you can achieve this formula. So we assume in low frequency that the current in the collector current, the drain current, drain source current is constant in this region. But in high frequency model, actually, okay, so for a small signal model of a low frequency NMOS, you can see that this is the model for NMOS. We can just say that by changing the VGS, we can change the current in the collector. Done. So there is no resistance between drain and source. There is no resistance between gate and source. Nothing. This is just a frequency model. The input impedance of a NMOS is infinity, and then the output impedance is the impedance that you put in the collector. Done. And then again we calculate the transconductance as the partial differential of the current, the drain current divided by partial differential of the voltage that we apply to the transistor, and then we find the value for the GN. Again, you see that it is dependent on the point that we are doing the biasing. It depends on the ID, and it depends on the VGS. Okay? We have one effect as the channel length modulation. So channel length modulation means that when you apply the VDS, so the length of the channel that we have is changing. Why? Because the depletion layer, if I want to show you on this slide, yeah. So here in the channel that we have, here is your channel. So when you increase the voltage at this point, from the drain to the source, then the shape of the channel would be like this. And then again, by increasing the voltage, then the shape of the channel should be like this. I mean that the length of the channel will change. And by changing the length of the channel, that L is changing. So it means that the current, and then by changing the L, we will see that the current is changing. So the current is not constant. And then we apply this as an effect of the channel modulation. And we say that, okay, for example, drain source conductance is lambda over ID. Lambda ID. Okay? So this is what we can calculate. I mean, then we have to put one resistor here and then say that, okay, partial differential of ID divided by partial differential of VDS. I mean, by changing the VDS in the low frequency model, the current does not change. But in the high frequency model, as the channel changing, the length of the channel change, then the current change, and then it shows some effect, and we define it as the RO. All right? So this is one effect. The next one is the body effect. So for the body effect, actually, the problem is that the MOSFET is not a 3-port device. It's a 4-port device. I mean that we have this substrate, and this substrate has a lead here, and it is connected as a bulk. Okay? So always we assume that bulk is connected to the source, but this is not correct. Okay? So bulk has voltage. So there is a voltage between the bulk and source. So we have a VBS here, and because of this VBS again, we define a new parameter, and because of that VBS, actually your transistor threshold voltage is changing because we are biasing your bulk, and your transistor voltage depends on the values of the phi and gamma, and then now it depends on the value of the VSB as well. I mean the new threshold voltage is the VT naught plus something, and these values for phi and gamma is in the order of 0.1, 0.2. Okay, but it shows, I mean, we define another parameter and we put the name as substrate transconductance, and this substrate transconductance we call it as GMB, and the value would be this. I mean, it is again the deviation of the bulk source voltage, how it affects the deviation in the current of the drain to source. Okay? And then the parasitics, what we had in the BJT as well. So anywhere that we have junction, we have capacitor. So the problem here that we have 4 leads, and the leads are close together, and I can tell you that. So look at these junctions here. So we have one junction here, we have one junction here, and then we have this gate to the bulk, and then drain to the bulk, and then source to the bulk. So we have 5 capacitors, 3 to the bulks, 1 from gate to source, and 1 from gate to drain. So 5 different capacitors we have, and we have to put them in our model. And then we put all these together. So the original that we have in the low frequency is only this. Now, and then I add this RO, and then I add this bulk here, okay? The capacitance between the source and the bulk, and also because of this VSP, we can say that we have another source of current here, which comes from this source, GMB. This is the source of current because of the source bulk voltage. And then 1 capacitor, 2 capacitor, 3, 4, and 5. So this is the high frequency model for a MOS transistor, and you can see that how complicated is this one comparing to this one. If we assume that there is no body effect, then we can omit this. I mean, body effect means the bulk and source has the same voltage. We can omit this, we can omit this part, okay? And then we can say that, okay, we have a capacitor from drain to source, so this is drain to bulk is changing to drain to source. And then the addition of these two, I mean the parallel of these two is a capacitor from, for example, gate only to source. Okay, so these two in parallel is this one, and then we have this capacitor. This is again very important because it gives you feedback from the drain to base, and it could be dangerous. We have the original current, and then we have this RO because of the channel modulation effect, and then we have this capacitor. So this is a kind of simplification in the model, high frequency model. Okay? And all these values that I calculated is in the saturation region. So you should consider that. Okay. Okay. So, as an example, for example, we have a MOS transistor, we have a DC voltage at the gate, and then also a VCC here. So here is VDD. To bias this transistor, we put a drain resistor for biasing. So we calculate the V out, and then if we want to find the gain of this transistor, the gain of the transistor is the deviation in the voltage output divided by the deviation in the voltage input. So we have to just do a partial differential of the V out based on V in, which is the VGS. So V in is VGS, okay? And then you can achieve this equation. Or simply you can go to the high frequency, the high frequency model, and then put these two values, model this. You can see that the V out equals to the current multiplied by the impedance in the drain. So the current is minus GM VGS, and VGS is V in, and then the output resistance also is this. And assuming that RO is infinity, again we achieve the same value. So you can go through any of these two. So we have exercises. Before that, I would like to go through the quiz, and then if we have time, we will come back here. If not, I will upload the result. I think we have time. All right. So just please. So please log in into this website. And enter this code. Okay, I will open the question for you, and you have 1 minute to answer. The question is now open. I think. Do you see that? Do you see the question in your Phone, all right, good. And you have the question also here if you want to, because some of the questions has graph, so the website is not, I'm not able to make graphs there, so I put the graphs here, and it seems that you can see that how your Okay, everybody answered, or is there anybody who didn't answer yet? Yes. All right. So it is about the TEM, wave propagating in the air. So it says that each of these is greater. And why the D is not there? What's the problem? I'm sorry that why the question is... Okay, it seems that the question is not complete in the PowerPoint, but you have the question there. So it says that each of these is greater in 3 gigahertz than 1 gigahertz. Is it done? Okay. So I'm closing the question. And then, all right, let's... Sorry, let's go back. To this slide. All right, as you can see, the phase velocity is dependent on the materials that we have. So the phase velocity is frequency independent. The phase velocity in the air is c, as you mentioned. It's 3 10 to the power 8 meter per second. Okay? So the phase velocity at 1 gigahertz and 3 gigahertz is similar. So it's not A. Okay. And then the intrinsic impedance, again, is constant because it doesn't rely on the frequency. It's constant. It is a square root of mu naught divided by epsilon naught, and for the air it is 377 ohm. It's constant for the air. But the propagation constant, which is what we are interested in, is dependent on the frequency, and by increasing the frequency, the propagation constant decreasing. So at 3 gigahertz, the propagation constant is higher than the 1 gigahertz. So by increasing the frequency, the lambda decreasing and the propagation constant increasing. Okay? So the correct answer is C. Any question on this? All right. So we are going to the second question. So second question is open now. And it says that in this graph, This graph could be which of the following, I mean, this graph shows the performance of which of the following components. It could be a resistor, it could be a capacitor or inductor. So is there anyone who didn't answer yet? No? Everybody answered? So I will close the test. All right. As most of you already answered correctly, so what we have here actually on this graph, if I want to show you, so in low frequency it shows a kind of constant resistance. So it means low frequency we have constant impedance. So we have a constant value of resistance or reactance. But none of the capacitors or inductors shows a constant value in low frequency because they are dependent on frequency. The value, one of them is j omega L and one of them is 1 over j omega C. So in the low frequency it's constant, so it's resistor. And then when the frequency increases, then the capacitance got a dominant behavior, and then after the resonant frequency, then the inductance of the leads or the inductance of the coil, those are dominant, and then it shows a kind of inductive behavior. Okay? Any question? And the last one. So the last question is open, and it says that assume that we have a MOS transistor and it is operating in the saturation region, which is what we are interested, and then the VDS is constant. I mean, we are working at one VDS point. So which of these graphs, I mean the GM, shows the function of the GM based on the override voltage or the VGS minus VTH. I mean the voltage that we apply to the base, which of them shows the dependence between the GM and VGS. All right. Is there anybody who didn't answer yet? One. Is it done? So please pick one because I want to close it down. It's regardless of what is your answer, we can follow. So I'm closing the test. And, all right. Let's back to the slide. So the formula for GM is this formula. Is 2ID divided by, do you have 2ID divided by VGS minus V threshold, okay? But the problem is that this ID is itself depends on VGS. I mean, the formula for the VGS, for the ID itself is VGS divided by V threshold squared. So if you put this formula in here, you see that the GM equals to something to, for example, K multiplied by VGS minus VTH. Okay? So it has a kind of linear relation. I mean, by increasing the VGS minus VTH, then you will achieve higher GM and higher gain. So this is what it should be. I mean, by increasing the voltage at the input of your transistor, you will achieve a higher gain. And so the A is the correct choice. Okay? Any question on this? Is that clear? So I think by 5:53 we will be finished. So I will upload the answer for the exercises. I try to solve one or two of them next lecture at the beginning very